understand the concept related to random variables. Like, that was kind of tough because I'm trying to explain to you that when you draw from the population and make a sample, you want that to be as random as possible. Process you're analyzing. A random variable is something being drawn from a pile of dung that's being repeated with a certain frequency. There's a structure to the frequency. It's not just noise. But anyway, it says, okay, so here, the table on the right, what do we call this kind of distribution where it's fixed amounts for 1, 2, 3? But what I mean to say is that we have 0 girls, 1 girl, 2 girls, 3 girls. We don't have anything like 1.5 girls. There isn't. We don't know what that means, unless the other half is dead, right? So this is a breaking down into what? Discrete numbers. There's no girls. I'm not going to try to find the probability of half a girl. You understand? These outcomes here can only be in whole numbers, integers, or in this case they're called natural numbers. And then they happen with this probability. So what kind of distribution do we call this? Good, you all got it at the same time. They're called a discrete distribution. Discrete. I know, it's exciting. What is not a discrete? Yeah, that's right, it's continuous, but why is it continuous? Because if I'm talking about people's height, well, it could be any kind of measurement. It just depends how sensitive the measurement is, right? You could have somebody that's 3.5 feet. You could have somebody 3 3/4. You know what I'm saying? The possibilities, that's called a continuous distribution. This is discrete. How about throwing a dice? What's the probability of a fair dice coming up? 1/6. How about a number 1 coming up? 1/6. Number 2? 1/6. 1/6, right? Is there such thing on a die between 1 and 2? Is there a 1.5 on the die? No. If you use a icosahedron, it's a 20-sided object. Dragon and Dungeons and Dragons, they roll this. Okay, so you have a conahedron. A icosahedron is a 20-sided. Okay, is that discrete or continuous? Well, I have from 1 to 20. Yes, that's what an icosahedron is. It's 20-sided. Okay, can you have 1.5? No, it's discrete too. It's going, because what is the probability of getting a 5 on the Dungeon and Dragon thing? Yeah, icosahedron. Icosahedron is actually the caspid. Have you ever heard of the word caspid? The outside shell of most viruses are the icosahedron, believe it or not. They're formed geometrically like. Well, I'm talking about real viruses. You really wouldn't want to roll for those. But I understand what you mean. Now, what I'm saying is that these are measures of a distribution that cannot get intervals in between these things. And that's how you can distinguish between continuous distribution or discrete. There's a whole branch of mathematics called discrete mathematics. Computer science uses a lot of discrete mathematics because the nature of a computer is what? A lot of it, processing, is either 0 or 1. Now, you got quantum computing coming. You got 0, 1, and you got maybe somewhere between 0 and 1. You have superposition. You can be at 0 and 1 at the same time with a quantum computer. Okay, so let's see what it has here. It says, table lists the probability of corresponding numbers of girls in 3 bursts. Okay? So we have 3 bursts. Now, what is the random variable? What is the possible values and its values numerically? Okay, so choose the correct answer. What is the random variable x? It's whatever pops out of the lottery. You're waiting. What is the x value? What is it going to be? What is it going to be? And then pop comes out. But when they start popping up, it's kind of like popcorn with a certain frequency. Then you can use that information to predict. This says, okay, the random variable x, which in this case is the number of girls in 3 bursts. Okay, what are the possible outcomes? None of them are girls. 1, 2, 3, or 4. Look, what does this tell you? The probability of getting 1 out of 3 is saying, in other words, what's the probability of you getting out of 3 3 boys and no girls. 1 girl. In this case, it'd be 2 boys. You see what I'm saying? And so now we got 3 girls. It's a 0.25% now. So look what it's happening. It goes 1.25, 375, 375, and we're back 1.25. Okay. So it says the random variable x is the number of girls in 3 bursts. So what are they? Here are the possibilities. The values of x are. Look at what your random variable is. Your random variable isn't the probability. It's the total number of girls. You want to know in what frequency is this happening? Now, how do you think they might have come out with that number? 0.125. Well, we can talk about listing the sample size. What is a sample size? In this case, well, look what we can do. Let's see, I'm not sure if they did this or not, but let's say we draw 3, and we find out that a possibility is that you got boy, boy, boy. Oops, right? And then you could have girl, boy, boy. Correct? And we could have boy, girl, boy. And we could have boy, boy, girl. And we can have, so now I can have what? Girl, girl, or girl, girl, girl. Could have what? Boy, well, I got it already. So let's see, what am I missing? So I got girl, boy. I got boy, girl, boy. No, I got that already. I got girl, girl, boy. Do I have girl, girl? No. So what do I need? I need a girl, girl, boy. I don't have that, do I? And now I could also have, girl, boy, girl. Do you see these are different, right? Because it matters. The order matters. You see what I'm saying? So I have 1, 2, 3, 4, 5, 6, 7. Let's see, what else am I missing? Anybody see any? Girl, girl, boy, boy, girl, girl. How about boy, girl, girl? Yeah. I don't have boy, girl, girl. What do I got? 8? 8? I do? You count them? I have to count all of these. 1, 2, 3, 4, 5, 6, 7, 8. Yes? Okay. So, what's the probability of getting no girls? Oh, well, that would be the probability of getting all boys. Correct? What's the probability of getting all boys? It's going to be 1 out of what? What is 1/8 in decimal? What's 1/8 in decimal? Wow, you didn't know you had to use math class. Anybody know what 1/8 is? Come on, 1/8. I mean, suppose your life depended on it. Don't you know? Don't you know if I write a fraction, a divided by b, you put a in the box and b goes here? Remember that from first grade, second, third? It's like, ugh. Right? What goes in here? What is it? Oh! Wow, weird. Okay. So, now, what is that? We have to be careful. Now, how about getting 1 girl? Well, how many of these have 1 girl in them? Oh, well, there's a girl. There's a girl. Yep. 3 of them? Where's the 3rd? 1 girl, 2 girls, 3 girls. Guess what? What are your chances when you turn it off? I don't see any more. Yeah, there are 3. There's a girl, and there's a girl. 1 girl. Okay, so if I turn off the lights and spin you around and you grab 1 batch of these, what's the chances that you're going to get one of these 3? 3 out of 8. What is 3 divided by 8? I know, it's another tough one. You have to take 3 and put it in a box and divide it by 8. Well, it didn't work. But hey, what is 1/8? Can somebody tell me what 1/8 is? I'm pointing at it. So what's 3 of them? Why do you say 0 in the front? It's like saying $0.37. I mean, I don't know why they do that. It bothers me. But it's true. I mean, I can say 0.125. It doesn't matter how many zeros. You understand? So guess what? This says 0.375. What? What? Funny? You're laughing. You're smiling. Is it about girls or what? Okay. So do you see where these numbers are coming from? Does anybody see where these numbers are coming from? They're coming from that I gave the whole sample, right? I had to figure out all the possible ways to do it. Guess what that is? 8 is my sample size. A good idea of that. So let's go to the next. High tech is supposed to work. Okay, now for 100 bursts, the probability of getting exactly 55 girls out of 100 bursts is equal to 48%. Notice it's less than 50. Remember I kind of explained why? Boys like to kill themselves. Okay, what is the probability of getting 55 or more girls? You understand? That's a different question than getting exactly. You see the word exactly? Okay, and this is 55 or more. Is that probability? Okay. 100 bursts significantly higher than girls. Well, is 55 girls in 100 significantly higher? I don't think so, do you? I mean, it's pretty close. I know. Which probability is relevant to answering the question? Consider the number of girls to be significantly high if the appropriate probability is 0.05 or less. So the probability of this and this, so 55 girls, it's not significantly high because the number of girls, because the relevant probability is greater than 0.05. So they're giving you some kind of test. If it's better than this, then we say significant or not. Does the table show a probability distribution? How can I test to see if it's a true probability? That's right. 100% if you add all these up. What else? Well, it can't be negative, and it can't be bigger than 1. So if it adds up, I don't know. Does it? You know, there's 3 and 3, that's 6. And then that's 30. That's 150, actually, isn't it? Twice, 300. Okay, so 3. Yeah, I'd say it's pretty close, isn't it? Anybody care to venture? Okay. Guess what? It does. This is too easy. I need harder material, huh? Let's see what else we got here. What are we going to use? Okay, let's try this one. I don't know what it is. Determine the potential. Okay, I got to get on to the next chapter, so that's nice. Ted is not particularly creative. That's a good start. He uses a pickup line. Hey, you could use statistics, guys, on your pickup lines. See, like, what helped me, in case you want to know, is I would go to VAR or something, and then I would pick a, like a piece of paper or napkin, and I would draw a girl I'm interested in, and then I'd give it to them. I know, but they're drunk. And the thing is, I start out with a question. I always ask them if they're from Finland. Are you Finnish? Why do you think I'm Finnish? They love that. Okay. Now, here we go. Okay, so is this thing? Well, the table does not appear to be a probability distribution. I go on to the next. Okay, expected value. Remember I was talking about expected to win? Okay, how about this one first? Use probability to determine whether or not an event is significant. We did that already. Okay, find the probability of getting exactly 4 sleepwalkers. And then find the probability of getting 4 or more. Okay, so which probability is relevant to determining whether 4 is a significantly high number? Okay, this is okay. Here's about expected. This is called. I went over it very slightly, but it's called. We call this the expected value. Okay, that's determining what you think if you go to Las Vegas, and if you know the odds. Right, the probability of winning, then you can calculate what you're expected to win at the end of your session gambling. State pick 3 lottery, you pay $1.33 for a sequence of 3 digits from 0 to 9, such as 588. So if you if you select the same sequence of 3 digits that are drawn, you win $467.24. Complete part A. How many different selections are possible? How do you think they got 1,000? Do you think they made it up, or? Okay, how about this? Let's say we have, we got three select. Let's say you have a briefcase, and the briefcase has a security lock in it. Yes? Is that right? Somebody say yeah. Okay, now, how many ways can the first number come up? It goes from 0 to 9. How many is that? It can come in one of 10 ways, right? Say yeah. How about the next one? Well, we're allowing, in a sense, replacement, right? Because we're letting you reuse the number. How many ways can that happen? And what if we multiply those? 1,000. I'm telling you, if you have a briefcase with just 3 of these, if you want to guess at it and be lucky, there's 1,000 combinations of numbers, of sets of 3 numbers. Yes? No? Right. Now, if I didn't allow replacement, or I didn't allow you to reuse the number, this would be 10, 9. It goes to tell you, what do you think the probability of your telephone number? You have 7 of these, right? Let's say, well, if I'm not even counting the area code yet. Now, if you think about what are the combination of telephone numbers you can come up with? Well, what would this first number go? Well, as far as I know, I've never seen a number with 0 in the front. And I don't think I've seen it with a 1 either. So I might say this has one of 8 ways. But this guy might be one of 10 ways. You can reuse it, but there's some constraint on the first number, I think. Whatever it is. But you can get an idea of how many different phone numbers you might be able to get. So there it is, 1,000. What is the probability of winning? 1 out of how many? 1 out of how many? How many? Yes. What is 1 divided by 1,000? Yeah, 0.001. 10, 100, 1,000. Yes? No? Okay. And then it says, find the expected value. How much do you expect to win, given these kind of odds? Or you're going to, I'll show you here. Hold on. If you bet $1.33 on this thing, your expected value is telling you, it's already telling you, it's 0.086 of the loss. Which is better, which bet is better, $1.33 in pick 3 or $1.33 in pick 4? Yeah, they have the same odds of winning. It's okay? Let's do another more of this. They already tell you the expected value. The next ones, you're going to have to calculate the expected value. There's a 0.99. That's almost pretty close. That randomly selected 29-year-old male lives through the year. Whoa, that's a nice statistics for a life insurance company. Guess what? I'm going to charge you $25 a month or less because you're only 29 and probably in good health. You know, I don't expect you to die. Look at the chances that you not die. If you realize when you get life insurance, you're betting against yourself. You're saying, I bet I'm going to die before my time. And they're taking your bet. Oh, I don't think you're going to die right away. But I'm 89. Oh, hell, your premium just went way up through the roof. We still don't think you're going to die, but you're paying $100,000 a month. There it is. The value of corresponding